a list example of finding centroids of compound or composite shapes. So this time what we've got is a section of HVAC pipe, so that would be carrying, or it might be carrying cold water, hot water, it might be carrying cold air, hot air, so heating, ventilation and air conditioning systems. And so it's a section of pipe, maybe we're thinking about where to support it or something like that. And so I'm just going to adjust this a little bit, it's kind of the wrong, it's better. And so often when you're talking about pipe or rod or even sections, like box section that's long and thin, what you can do is rather than trying to figure out your center of gravity using two-dimensional shapes or even using the three-dimensional shapes like we did in the very first example here, what you can do is just represent them as lines. And then you would be going to, let me see if I can find this. So we would be going to this sheet where it talks about curvilinear shapes. So curvilinear just means curves or lines. And so this we're looking at, so that's no longer a two-dimensional circle, it's just like a circular pipe. Okay, there's nothing in the middle here. That's what these shapes are talking about. This is a semicircular bar or a pipe or a section or something like that, and that's where the centroid of this would be. So what you see there is kind of interesting. If you were looking at this shape, there's actually no centroid on the shape. You couldn't hold this and it would balance at a point on the shape. To get it balanced in all directions, the centroid is actually outside the shape, which is a little bit counterintuitive, but it's the way it is. And so, like, you could balance this, but it would fall down. It wouldn't balance in the other direction. I haven't explained that very well, have I? Maybe I'll make a wee video sometime and just show you what I mean by that, what I mean by it doesn't balance anywhere on the shape itself. I'll have to think about how I can support something off the shape. Anyway, I'll make a video for that at some point. So let me close that. So what we're doing is we're just representing these by lines. So when we're doing the centroids, we're going to that other page for the centroids of these. And so it's made up of a couple of shapes. We've got a straight line, then we've got a quarter circle, then we've got another straight line to represent this pipe. The pipe weighs 2 kilograms per meter, and it's constant. So that means that we can use an equation that's just using the length. And so I think that was like the third equation or something like that. Let's just go back to those and have a quick look. So we had all these different options. So we're now looking at curvilinear elements. We've got constant mass per unit length. Then we can use this formula. If it wasn't constant mass per unit length, if each one had a different mass, for example, if they were different sized pipes all joined together, you would have to go back to this equation and work out either the mass or work out the weight of each section, and then use one of these formulae to calculate the centroid of the composite or the compound shape. So let's go back again to here. So other than that, the process is exactly the same. We're not taking anything away this time. We're adding 3 elements. We've got a straight line, we've got a quarter circle and another straight line. The centroid of a straight line, it's almost just like your ruler. It's just in the middle of the straight line. It's 1.5 meters long, so it's going to be about 0.75, so it's going to be there somewhere. For the other straight line, it's just halfway along the straight line is where the centroid of that would be. It would balance in any direction. So the centroid would be there. For this one here, I'm going to, probably in the exam, I won't expect you to remember the centroids for the curvilinear. I would expect you to try and remember all the two-dimensional shape centroids. But for these curvilinear ones, not so much. If you need to use that in an exam, I'll give you it. And so let me go back to here. Go back to those formulae. I think it's something like 2r upon pi or something like that. So let's have a look. It is 2r upon pi. Okay, so we've got a quarter circle, and it's going to, so the centroid is 2r upon pi. Pi r upon 2 is the length of that line. We're going to need that because the question asked us to figure out the weight as well. That makes sense. 2 pi r is the perimeter of a circle, so a quarter must be pi r upon 2. Okie dokie. So back we go. I need one more of these. And so we're going to have another centroid that's kind of in here somewhere. 2r upon pi, so it's a bit less. So this would be r, if you know what I mean. The centre's here. So it was r here. 2r upon pi is roughly 2 over 3, so it's about 2/3 of the way along. So it's going to be right in here somewhere. So this would be R all the way up here. It's going to go at 45 degrees because of the symmetry of it. So somewhere here, something like that. Now, so what I'll do next is I'll run through that, do the same as last time. I'm just going to write on the positions of all these things on here. I'll write out my x's. I'll probably come back when I calculate, probably not. We'll calculate the lengths of all these. That's pretty easy as well. And then we'll come back to find the centroid and find the weight. Oh, interesting. Determine the weight, not the mass, the weight. So we'll come back and calculate that. Okay, back in a minute. Okay, so I've calculated all my positions of all the centroids of each of those lines or curves, so each of those curvilinear shapes. So I've got the x coordinate of each of them, the y coordinate of each of them, and then I've calculated the length of each, so just using the formula from the cheat sheet there, and calculated the length of that one as well. So now I'm going to start adding them together. I've added together the lengths. Now the formula we're using this time, because all of the weights per unit length, so the weight per meter of each of these pipes is all the same. In other words, it's all the same size of pipe. The formula we're using is the centroid of the composite shape is equal to the position of the centroid of each shape times its length divided by the total length. And similarly, the y position of the centroid of the whole shape is equal to position of each shape divided by the total length. So I'll just calculate these two next, and then we'll come back to finish it off. Oh, no, I'll just calculate that and I'll do the calculation because it's not too difficult, similar to what we've been doing before. And then we just got one other part, which is to find the weight of the pipe. So back in a minute. So we figured out the position of the centroid, or the center of gravity of the overall shape, the centroid of the shape, the center of gravity of the pipes, roughly. It's a bit of an approximation, but it's close enough. So you're just basically ignoring the width of the pipe, really, or the diameter of the pipe. And so where's it ending up? So it's ending up at x coordinate about 1.4. So 1.4. 4 is about there somewhere. And the y coordinate's 1.15, which is about here somewhere. So that's the centroid of this. And so what does that tell us? It's counterintuitive because it doesn't actually sit on the shape. But if you were to put some light struts out to that, like easy strut or something like that, some light struts out to that, and if you put it like that and supported the pipe at these points using a cable here or something like that, then that pipe would balance at that position, wouldn't rotate around anywhere. The struts would change it a little bit, but if they were light compared to the weight of the pipe, then that would work. That would be where you could hang that without putting any stresses on the pipe itself. So that was that. So we figured out those. And then the last thing it just asked us for the weight, the total weight of the pipe, I think. Determine the weight and center of gravity relative to A. So for the weight of the pipe, so we've got length, or we've got mass per unit length. So the weight per, let's just write it out so someone can understand. Mass per unit length is equal to 2 kilograms per meter, I think it was. Let's just check that. Yep. So the weight per unit length, well, we just times it by gravity. So weight per unit length, they haven't told us to do it approximately. So this is different from the unit weight. The unit weight's the weight per unit volume. This is the weight per unit length. So is equal to 2 times, so change kilograms to newtons, times it by acceleration due to gravity, 2 times 9.81, which equals 18.62, I think. So 2 times 9.81, 19.62. So 19.62 newtons, we put in kilograms, so it's going to be in newtons per meter. Looks about right. It's quite a light pipe. It must just be a foam pipe or something like that. So weight per unit length, that's all good. So now we want the weight itself. So to get the weight, that's weight per unit length. So you just want to do weight per unit length, 19.62 times the total length, which is equal to, we've already calculated that, so it's 19.62 times total length of that pipe was 3.285, which is equal to 64.5 kilograms. 64.5 kilograms. Just checking I've got that all right. Okay. So, I don't know why I'm saying, I know I say so a lot. I'm going to start writing it as well. Position of center of gravity is x equals 1.386, round to 3 significant figures for our final answer, 1.39 meters, y, position of the center of the whole shape is 1.15 meters as per axes in above sketch. And weight is equal to 64.5. Does that seem about right? Okay. Ooh, what an umpty. That was in, so this was the weight per unit length. I just think it seems an awful lot given it's only 2 kilograms per meter length. So just seen that I've made a mistake there. So that's newtons now. That makes more sense. It's about 6 kilograms, 64.5 newtons, because I'm thinking this is, just from the sketch, 1.51, a little bit more. So it should be a couple of kilograms, a couple of meters, something like that. It was 3 meters, 3.285 meters. So the weight's 64.5 newtons, which is about, just doing it in my head, 6.45 kilograms if you just divide by 10. So that makes sense. Done. Okay, so that's everything for center of gravity, but we'll now look at one other way where we use the centroid when we have got distributed forces. So let's have a look at that now.